Remember we talked about how Ohm's law cannot be applied when we don't know the voltage or current directly affecting a resistor? So how can we get around that? This is a simple single loop circuit. As the name sounds, there is just one loop with resistors and a voltage source connected. What we want is to figure out the current flowing through this circuit. So how do we figure that out? Notice how if some current, let's label it I, is entering the resistor here, then it's the same exact current exiting. In other words, if we use KCL, we can show that the current going through this resistor is the same as the current flowing through this one. In a single loop circuit, each of these elements will have the same current flowing through them. We call that a series circuit. In other words, because these elements carry the same current in a single path, they are connected in series. But how can we figure out the voltage across each of these resistors? One way is first using Kirchhoff's voltage law. So let's go clockwise, and we have the voltage of resistor 1, and then 2, and then finally the source voltage, which we entered from the negative side. Let's isolate for the source voltage. From Ohm's law, we know that this voltage is equal to the current times the resistance, and the same is true for this one. So we can write our voltages in terms of current and resistance like this. Now we can isolate it for current. This allows us to find the current in the circuit. Remember, since this is series, the current is the same for all of our resistors. Knowing the current, we can figure out the voltage across resistor 1. The same for resistor 2. These equations are what's known as voltage dividers. In simple terms, we can see that the voltage is divided between the two resistors proportional to their resistance. Now the most important thing to keep in mind is that while the current is the same throughout a series circuit, the voltage is not. Now it's okay to use voltage dividers when we have simple circuits, but what if we have a lot of resistors and we need to figure out the voltage in each one? Since we know the current in a series circuit is the same for all the elements, we just need to figure out that current value. Then we can apply Ohm's law and figure out the voltage at each element. So in this circuit, we need to find the current. How can we do that? A way to do it is to actually combine resistors that are in series. All of these resistors are in series, and we can replace all of them with a single one. The value of that single resistor is equal to the addition of all of these resistors. So our new circuit looks like this. This way, we can easily find the current by using Ohm's law. Since we figured out the current, we can apply Ohm's law to all of these resistors we had and figure out each individual voltage. If we wanted to know the voltage of resistor 1, we use Ohm's law, so V equals IR. And we already figured out the current. We can do that because we know that the current in a series circuit is the same for all the elements. Don't worry, when we cover examples, all of this will make more sense. We can also combine voltage sources. So here is a new circuit with multiple voltage sources. Let's assume a current flow in the clockwise direction. So our new single voltage source is equal to the addition of all of these voltage sources. But you have to be careful to note the positive and negative signs. So remember to check whether our assumed current enters the positive terminal or the negative terminal, as this determines the algebraic positive or negative sign. For example, these two voltage sources will be considered negative since our current enters the negative terminal. What about when we have circuits like these? If you look, you can see that the current has more than one path to travel. If we got rid of this conductor, the current can still traverse the circuit, and if we remove this conductor instead, it can still go around. This is called a parallel circuit. Let's apply Kirchhoff's voltage law to this loop, and we will go clockwise. Let's solve for the voltage of resistor 1. Now we can write a KVL for this loop, again going clockwise. Notice we get the same voltage for both resistors. This brings up an important point. In a parallel circuit, the voltages are the same across all the elements. Here is another parallel circuit, also called a single node pair circuit. Let's focus on this upper node and write a KCL equation. We have current coming in, and then it's divided at this point into two paths. So we have I1 and I2 leaving. Let's isolate this equation for our source current. Now remember, the voltage is the same in all the resistors, so let's write our current as a function of voltage and resistance using Ohm's law. Let's factor out the voltage. Now to make our math a bit easier, we're going to simplify our fractions. So we can write our equation like this. Let's isolate this for voltage. Now we can go back and isolate our currents. So current 1 was equal to this, and we can plug in our voltage. Let's simplify. The same can be done for I2. These equations are called current division equations. You can see that in a parallel circuit, the current is not the same for each branch. Rather, it's divided based upon the resistor values. But as with voltage division, this is tedious to do when we have multiple resistors in parallel. Now we know the voltage is the same in a parallel circuit, so we just need to figure that value out, and then we can apply Ohm's law to get the currents in each branch. So the solution is to combine resistors in a parallel circuit. Then we can solve for the voltage and apply it to all the resistors. So how can we add the resistors? Well, in parallel circuits, the total resistance is equal to this. It's really important to note the 1 over the total resistance here, because once you add up all the resistors in parallel, you still need to solve for the total resistance by dividing 1 by the total added resistance. That's a mouthful, but to illustrate this, I'm going to replace these with numerical values. So let's add it all together. Notice how we still need to solve for Rp by flipping both sides to get Rp as a numerator. In other words, you divide 1 by the value of the resistance we found. So here, all of these resistors can be replaced with one resistor with this value. Okay, back to variables again. So once you find the parallel resistance, we can solve for the voltage using Ohm's law. Then we can figure out the current flowing through each conductor by dividing the voltage by the resistor value. Again, this will make a lot more sense when we cover examples. Just as we did for voltage sources, we can add current sources together. You just have to be careful with the direction they're pointing. So in this circuit, we can add all of these together, noting that the second current source is pointing down, so it'll be negative. So just to recap, in a series circuit, we add resistors together like this. And in a parallel circuit, we add resistors like this. But what about when we have a mix of both in a circuit? So when we want to figure out the equivalent resistance between points A and B, what we need to do is combine all of these resistors into a single one. So looking at this branch, notice how the current has nowhere to go from this point to this point. In other words, the same current has to go through both resistors. So these two are in series. So we can add them together and replace it with a single resistor. Now if we focus on this node and look to see where the current can go, we see that it's split into two. In other words, there are two paths for the current to travel, so that means these two resistors are parallel. So we can add them together using parallel resistor addition. Now we have three resistors and only one path for the current to travel. So that means all of these resistors are in series and we can add them all together. The value of this resistor is the equivalent resistor value between points A and B. When solving problems, you will need to label the polarity for the voltage on your resistors. Now resistors don't actually have a polarity in real life, but when we solve problems, we need to assign positive and negative sides for our algebraic equations to work properly. The general convention is to assign a positive to where the current enters. So here, you first make an assumption about the direction of current. whether it's clockwise or counterclockwise. Let's say you picked clockwise. Now you will label the voltages on the resistors as positive on this side because that's where the current would enter from. Now let's say you picked the opposite. You think the current will go in the counterclockwise direction. Then you will pick these sides to be the positive sides. Regardless of the direction of current, the positive side will be where the current enters from. In the very last example, we will go over a scenario where we guessed the wrong direction for current. Now that we know how to combine all sorts of different circuit elements, we can use those techniques to solve for unknowns on circuits. We will go over a few examples to cover different types of scenarios, so let's get to it. If you need a refresh on Ohm's law and Kirchhoff's laws, please watch the previous video as we need to use these to solve problems. Let's take a look at this question where we need to figure out I0 in the circuit. So the way to solve this problem is through combining resistors. We see that these two resistors are in parallel since current has two paths to go through. Let's combine them. So remember, it's 1 over 4 plus 1 over 12, which equals 1 over 3, and then we isolate for Rp by flipping both sides. Now we can see that these two resistors are in series. Let's add them. At this step, you can use the current division equation to solve, but let's go through how to solve a problem by going to the very basic circuit and using Ohm's law. Now we have two resistors in parallel again. So let's add them together. We end up with a simple circuit and we can solve for the voltage in this resistor using Ohm's law. The current will be traveling this way, so our positive side for the resistor will be here. I converted milliamps to amps and kiloohms to ohms. Let's solve. Now that we have the voltage, let's go back to the previous step. Keep in mind that we added two parallel resistors to get to this resistor. That means the voltage is the same for these two resistors because they're in parallel. Again, in a parallel circuit, all the elements have the same voltage. The current will enter from this side, so our positives and negatives will look like this. Now we can solve for the current in this conductor since we have the voltage and the resistance. That gives us 6 milliamps. Now we go back one more step. Remember, we added two resistors in series to get the value of this resistor. And in a series circuit, the current is the same for all elements. So that means the same 6 milliamps is flowing through this resistor and this one. That also means we can solve for the voltage in this resistor. We get 18 volts. Now we can go back to our original circuit diagram. The voltage is the same for both of these resistors since they are in parallel. So let's solve for the current one last time using Ohm's law. We get 4.5 milliamps and that's our answer. Let's take a look at this question asking us to find the equivalent resistance between points A and B. So we just need to combine resistors. We can start at the bottom corner because current only has one path to travel through, so we know they are in series. Let's add them together. Now we see that all three of these resistors are in parallel. If it's hard to see, remember that conductors are bendable, so you can move them around in your mind. Now we look at this corner and we see that these two resistors are in series. So let's add those together. Lastly, we see that all three of these resistors are in parallel, so we can add them like this. Let's take a look at this question where we need to figure out I1 and V0. We can start combining resistors. Notice how these two are in series. Let's add them together. Just a note that you can do multiple combinations at once to solve these faster, but in this video, we will take it step by step. Now we see that these two resistors are in parallel, so let's add those together. Lastly, we have these two in series, so we can add those together. Now that we have a simple circuit, I'm going to assume a current direction like this and label positives and negatives on our resistor. Let's use Ohm's law to figure out the current in the circuit. We get 2 milliamps. Now we go backwards. The current is the same in a series circuit, so the current in both of these resistors is 2 milliamps. That means we can figure out the voltage of each one, but we really only need the voltage of this one. So let's use Ohm's law and get that value. Now to get this resistor, we added two resistors in parallel. That means both of those have the same voltage. So the next step is to figure out the current flowing through each resistor using Ohm's law. Let's do this conductor first. Next, we can do this one. The 1.33 milliamps is actually the current of I1, so that part of the question is solved. To get V0, we just need to figure out the voltage of the 4K ohm resistor. We know the current passing through it because we added these two resistors in series to get the 12K ohm resistor. So let's use Ohm's law to figure it out. And those are our answers. Let's take a look at this question where we are told the voltage of this 5 ohm resistor is 15 volts. And we need to figure out the voltage of this power source. The way we're going to solve this question is to write a KVL for this loop here. But for that to work, we need the voltages of these resistors. So that's where we're going to start. The first step is to label how we think the current will flow, and then label the positives and negatives on our resistors. We will assume all current flow to be clockwise. Now from the question, we know the voltage of this 5 ohm resistor. That means the current flowing through it can be found using Ohm's law. We get 3 amps, and that's the value of I5. Now let's consider this node here and write a KCL equation. We have I4 coming in, and then 2 amps leaving, along with our I5 value. All of that is equal to 0. We're assuming currents coming into the node to be positive, while those leaving the node to be negative. Solving gives us the value of I4. We can also figure out the voltage of the 3 ohm resistor using Ohm's law. That gives us 9 volts. Next, we will write a KVL for this loop here. Why? Well, if we figure out the voltage of this resistor, we can figure out I3, which will then give us I2. We will go clockwise for our KVL equation starting here. We have positive 9, positive 15, negative 8, and negative B for the voltage at the 4 ohm resistor. Solving gives us 16 volts. Now we can figure out the current using Ohm's law. So we get 4 amps for our I3 value. Next, we will focus on this node and write a KCL. We have I2 coming in and then 2 currents leaving the node. Solving gives us 9 amps. Using this, we can figure out the voltage of the 4 ohm resistor. We get 36 volts. Next, we need to write a KCL for this node here to get I1. So we have I1 coming in, then 9 amps leaving, and 3 amps coming in. We get 6 amps, which can then be used to figure out the voltage of our 4 ohm resistor. That gives us 24 volts. Now that we have the voltages we need for our KVL loop, let's write it. We will go clockwise starting from here. Solving gives us 84 volts. Let's take a look at this question where we need to find IS, and we're told that the 10-volt source absorbs 40 watts of power. I'm going to assume current flows to be clockwise and assign positive and negative sides to our resistors. Knowing that this voltage source is absorbing 40 watts of power, we can solve for the current flowing through it. Remember, power is equal to voltage times the current. Solving tells us the current flowing in this conductor. Since this resistor is in series with the voltage source, the current that's flowing in this resistor is the same, so we can solve for the voltage. Now that we have the voltage, we can write a KVL for this loop to get Vx. We will go clockwise. So we get 30 volts for Vx, which means we can figure out the voltage in the dependent voltage source. We can also figure out the current flowing through our 15 ohm resistor using Ohm's law. We get 2 amps. Now if we focus on this node and write a KCL, we can figure out the current coming in. We get 6 amps, which we can use to figure out the voltage in the 4 ohm resistor. Now we will write a KVL for this loop to figure out the voltage of this 6 ohm resistor. We will go clockwise. We got a negative answer. That means the voltage signs are opposite to what we assumed. In other words, this current here isn't going left to right, but rather right to left. But that doesn't matter right now. We will go with our initial assumption. We can now figure out the current flowing through the resistor using Ohm's law. We get negative 6 amps, again indicating our assumed direction for the current arrow is wrong. Now we can write a KCL for this node to figure out IS. We get 12 amps, and that's our answer. It's important to realize that your assumed direction for current does not matter, as long as you label your polarities based on your assumption, so current enters the positive side. After that, even if you get a negative value, follow through until the end and you will get the same answer. That should cover the types of problems you will face when it comes to adding resistors in parallel and series. Thanks for watching and best of luck with your studies.